Let me show you how to calculate the center of gravity of a system. We'll start off with a really simple system. We've got a couple kids on a teeter-totter, right? We know that they're going to balance when their center of gravity is directly above this log, okay? For example, right? Because that's one of the basic tenets of the center of gravity of an object, right? Is that it's the balance point, okay? And so, I never know whether to teach torsional equilibrium first or center of gravity. I chose torsional equilibrium first. And now we can use torsional equilibrium to solve this thing, right? So this kid here is exerting a downward force, right? And that's going to be, we're making a formula here, right? But it's m1 times g, and the distance it is from the pivot point is x, we'll say, okay? And then that's going to tend to rotate it anti-clockwise, so we'll say it's negative, right? And then we have this guy over here, right, who is a distance of L minus X from the pivot point, right? Okay, if the total distance between them is L, right? And this torque here is, we've got a force of M2 times G, right? And then that's going to be at L minus X. And this is going to be a positive torque because this guy will tend to torque it positively about that point, right? So our torque expression looks like this. We've got minus m1 times g times x plus L minus x times m2 times g. And of course the formula I'm using more or less is that R times F is our torque, right? Okay, so here's R times F. Here's R times F. I'm doing it in different orders. It's very confusing, but there it is, right? Okay, and then that adds up to 0, okay? Now the next thing I'm going to do is I'm just going to, I guess I can cross off gravity, right? Okay, so we understand that this system, if it balances on Earth, it would also balance on the Moon and on Jupiter if it had a surface and all this stuff, right? Okay, so now we can just start busting stuff out. We go minus m1x, and then let's distribute this, right? Plus m2l plus, minus m2x. I'm just distributing this m2 times l, m2 times x, right? And that's 0. And then I can stick all the things with x on the right side. So I get m2l equals m1x plus m2x. And then if I just divide this by, if I factor out the x, right, m2l is m1 plus m2 times x, I get, ta-da, the teeter-totter equation. Okay, now what's funny is that x is the distance that the center of gravity is from m1, but in the numerator, and you understand why now mathematically, right? Because if I divide this, I get m2l over m1 plus m2. In the numerator, I've got the other mass. That's kind of interesting, right? Okay, but let me just say, I'm going to erase here in a second. Let me just say that this is actually a generalized form. It actually is this. X is actually equal to 0 times m1, because we're finding out how far the center of gravity is from the left side. Really is what we're doing, right? So it's 0 times m1 plus L times m2 over m1 plus m2, right? That's the real form of this thing. It's just that m1 happened to be right at the left side, okay? So you can generalize this formula, the general form of this thing, if you've got, m1, m2, and m3, okay? The general form is that it's m1 times x1 plus m2 times x2 plus m3 times x3, all over the sum of the masses, okay? Now, this x, really what this is it's a weighted, no pun intended, right, mass. It should be massed, right? It's a weighted average of x1, x2, and x3, and the weights are literally the masses. So for example, m2 is going to be more important in this average than m1 if m2 is larger than m1, right? Okay. This is not in your data packet, but it's easy to remember, I think. Okay, so we just have to remember that. Memorize that thing. All right, let's do an example of this. Let's find the distance the center of gravity is of this entire system from the left side. Okay, so let's see. the beam. The beam is 14 meters long, right? And it's a 45 kilogram beam. So I'm going to say that M1 is the beam itself, 45 kilograms. And of course, this is recursive. We're going to use a center of mass concept to solve for the center of mass, okay? And so the question is, if it's 14 meters long, where do we say the 45 kilogram beam is? Well, of course, it's going to be at its center, right? So X1 is going to be 7 meters, right? And that is because it's at the center of the beam, all right? And then M2 is going to be the 12 kilogram box. And X2 is, 4 meters from the left side. Okay. And then the 30 kilogram box is 13 meters from the left side, right? So M3 is 30 kilograms and X3 is 13 meters. All right, so now we just have to plug it into the fancy formula, right? Look at that, without even using the shift key. Okay, so XCOM is equal to 45 times 7 plus 12 times 4 plus 30 times 13 all divided by, cheated there, 45 plus 12 plus 30. Okay, now just be careful when you type this into your calculator. You can either do the fraction thing, the alpha F1 on your TI-84s with the new OS, and make it look like this fraction, and then you got no problems, right? If you are not so gifted as to have that fancy OS where you can make fractions look like this, you have to put parentheses in this, okay? You literally have to type something like this: 45 times 7 plus 12 times 4 plus 30 times 13, right parenthesis, divided by left parenthesis 45 plus 12 plus 30, right parenthesis. Okay, so let me just do that. That's the kind of calculator I'm using right now. So left parenthesis 45 times 7 plus 12 times 4 plus 30 times 13 divided by left parenthesis, right parenthesis divided by left parenthesis 45 plus 12 plus 30. Patumba, 8.655. $65517 meters from the left side. Ta-da. Yay. All right. I'm going to go through some examples here. The first two examples are not really like assessment questions, but they're interesting. The last three go through all three possibilities. So I highly, highly recommend that you look at the very last three of these examples that I do with the meter sticks and the clamps and finding the unknown and all that stuff. All right.